Well, hello friends. Welcome back to Emulator Hacking. Today we are going to continue the work that we started yesterday. So it's the user space emulator can now run our browser. And yesterday it was extremely slow. Today is still quite slow, but significantly better. So yesterday we went from 34 seconds page load time here to 1.6 seconds. And today I'd like to lower that further. So we kind of already know what the bottlenecks are, but let's still get a profile just to remind ourselves. And I'll just profile myself scrolling up and down on the web page here a little bit. And then we'll flip it upside down and we can see that soft MMU find region is now the dominant function in the profile with 37% of runtime spent looking up memory regions. This is something that has to execute every time that you do a read or write memory access. So it happens a lot. And just like the data structure from yesterday, it's again a vector of regions that we don't sort, and we just scan this thing. We have to scan this vector when we're looking for the memory region that corresponds to a given address. So obviously that's not very fast. We can see here that the function is really just a loop over the vector of regions and then comparing the address that we're looking for. So I'm thinking, wouldn't it be nice if this thing would run in constant time? I think that would be really nice. So there are a couple of different approaches to this, but I feel like the absolute easiest way would be to just pretend that we are a CPU and just make our very own sort of page mapping cache. A little bit like the TLB in a CPU, but it'll be different because I think when you're running the user space emulator, you're really only running one program, right? So if we want to have a pretty bulky data structure to cache page translations, I think that would probably be okay. So my thinking here is that we'll just make a map that maps every page space address to the region that is mapped there. And let's do a little math. So we have 4 gigabytes of address space, and the top 1 gigabyte is reserved by the kernel, so we have 3 gigabytes of address space, which is that many. And if we divide that by 4K, this is how many pages we have. So we need an array with this many entries. So I'm thinking, why don't we just do something like this? Region, like page to region map, something like this. 786432. Now that is a large thing. It's a 3 megabytes data structure, but I feel like this is going to be okay, because what is 3 megabytes really? It's not the end of the world, in this context at least. And if that's, I mean, it's a classic space-time trade-off thing, right? It's like, so we're going to pay 3 megabytes of memory, but it will give us constant time lookup of regions. So of course now we need to maintain this lookup table, page to region map. But really there are two points where we can add or remove a region to the MMU, and that's when we add or remove a region. So here in add region, I think we can iterate across the page index. Let's see. So I guess we want to figure out, wait, it has moved at this point. Let's not get ahead of ourselves. Region base divided by page size. And we want to go to, or actually, you know what? Let's simplify this a little bit. So we'll do it this way. And then page, first page in region is region base divided by page size. And then the page to region map. I already forgot what it was called. Page to region map is region, something like this. Yes. And then when we remove a region, we just have to take care to clear out these pointers. So same story, but we make them null. Okay. And then when you call find region, instead of iterating across all of our regions, now we just have to do page to region map, address, offset, and page size -1. And then we need to divide that by the page size. That's our index. Okay. Am I getting this right now? I hope I'm getting it right. We'll see. I feel like I'm messing something up here. Yeah, I did. All right. All right. What did we mess up now? I guess let's do one thing at a time. So page index is address, offset. Don't we have a page mask somewhere? Wait, this seems right. What's wrong with that? Anyway. Oh, wait. Am I doing this in some other stupid way somewhere? And regions. No, I'm not manipulating it anywhere. And I feel like these regions should be for page size aligned. If they're not, that would be an issue. So let's double check that. So we'll assert that the bottom bits are all 0. Something like that. We can insert that when we are removing one as well, because why not? Okay, so we're crashing. Soft MMU add region. Wait, why though? Okay, I'm just overlooking something now. What am I doing? Address to line, please. Line 46. Oh wait, we're calling find region and that's crashy then? Okay, so I guess I'm doing something stupid here, like forgetting to divide by the page size. Okay, so it's not aligned to the page size. That is very interesting. How is that happening? Why would we be having a memory region that's not page aligned? Stack. Oh, wait. Is it one of our own simple regions? Oh, right. We're just callocating that. Although that's fine because it's the base address that has to be page aligned. So wait, who's the page allocator here? I guess it's mmap has like a really crappy page allocator somewhere. New mmap region. How does this work? The base is provided. Okay. Final address. Round up to the power of 2. Allocate VM. Okay. So we need to make sure that the alignment is always at least page size. Okay. Yeah, we're gonna need to figure out what is going on here. So base is that's a very strange base address. What the heck? Oh, wait, we're not rounding properly here. The next address needs to be page round up. That macro is only in the kernel, I guess. Oh, we can do it this way. Yeah, this VM allocator is obviously stupid. It's just incrementing pointer. Still? So we're good all the way until here. What the heck happens here? Wait. This looks like an ELF header region though. 244, 244. Yeah. Okay. So when we create this region, I guess it's okay that the base is not completely aligned. We just have to mask that off. Yeah. Okay, I see. So, not that these changes are bad, but in an ELF executable, it just tells you like load this part of the executable at this virtual address. And these addresses might not be aligned. As you can see here, the virtual address where we're supposed to copy in the read-write segment of this executable, it wants a 4K alignment, but the virtual address where it starts is not 4K aligned, so that's something that we have to tolerate. So this check here is bogus. And let's see. Let's just print out what we're looking for then. No region for this. Is that good though? Should be at that index. So I'm just looking at like, are we forgetting the stack region? But the stack region is made here. That's that 1000. Oh, okay. So what is 2000? 2 fajillion. It's the TLS. Right. A TCB. It's a region that we make. Where does it go? We add it here. Well, we do add it. Okay, I'm confused. So let's just log what region we find. And these lookups seem pretty cool otherwise. Like you see the different addresses here and they all map to the same page index. So that part is good. And looking up this region failed. Wonder why that fails. Is it that it's so small? And we need to round up the number of pages when we add a region because it's less than one page. So this division here turns into 0. What do we normally do with that? We have something somewhere. Sealed it, right? Yeah. Yeah, that's more like it. So yeah, so the TLS region in the executable was less than a page in size. Let's take a look here. Yeah, so it's 8 bytes. So it doesn't. We can't like iterate to size divided by page size because then we just get a 0. So we do a seal div, which is just a division that rounds up. So I think we're good. Yeah, that works. Let's look at the browser. .3. Very nice. So down from 1.6 to 1.3 something. That's awesome. So obviously it's not going to be as big of a step as 34 seconds down to 1.6 seconds, but it's still a good improvement. So let's get a new profile here and just scroll up and down a bit to see what he's doing now. And where is find region? It is all the way down here, 1.8%. So no longer dominating the profile. Instead, we have emulator exec here at the top. So this is the main CPU execution loop. We inline a lot of code into this function. So this is where all of the instruction decoding and dispatch happens. So it makes sense for that one to dominate, but so like now it's maybe a little bit less obvious where to go from here. We can see that we have we can see that we have a crash. So can I get a profile viewer, please? Come back. Yeah, so we can see some sketchy stuff here. Now it's also including the leak checking, but let's filter. Yeah, so we can see some sketchy stuff here, like is readable, and it crashes when I click on it for some reason. I don't know why is readable is in the profile. I'm not going to click on it. Region is readable. Is readable. It's a virtual. Okay, so we're calling that a lot. That's heavy. Same with this writable. So those things could probably be optimized into using members or something like that instead of a virtual dispatch. Find region is probably fine where it is now. So let's maybe see if we can use the top functions mode here. So So what are some instructions? We have mov between register and memory, dominating the instruction list at least, 13.3% in that one. And the memory read is the heaviest part. And the malloc audit is the heavy part of that. And that's probably something that could be improved further, but that was the thing we worked on yesterday, right? Like making the malloc audit faster. And then we have push, 32-bit register. That's also like just memory write. Another mov, and then sign division, and here we have stasd and stasb. So these are essentially memset, and between the two of them, it's almost 5% of execution time, and those we can certainly optimize because right now when you do a memset inside of the emulator, then it will go like 1 byte or 1 32-bit word at a time, and like emulate every step of the way. And we could definitely move all the overhead of doing that to the front, so we could like validate that we're memsetting something that's like part of a valid memory region, and then we don't have to like revalidate for every step. Yeah, we could probably make these very, very fast. So right down here we have movsd, it's mov string double word, that's memcopy. But memset it should be very easy actually to do. So let's maybe do that, but let's commit first though. So yeah, and the alignment changes to allocator. Always make sure the crappy VM allocator remains page aligned. We don't want the next address pointer losing its alignment somehow. This whole thing should be replaced at some point. Or UE hosted programs. Since UE hosted programs won't be able to run forever with this allocation strategy. Yeah, because it will run out of virtual memory, right? If it just keeps incrementing the pointer that mmap gives you. Anyway, and then, yeah, so we're making this map. User space emulator. Add a page to MMU region, page address to MMU region, lookup table, lookup map. To make find soft MMU find region run in O of 1 time and constant or this patch invests 3 megabyte into lookup table. We track each possible page-based address and map them to the soft MMU region corresponding to that address. Or no. Yeah. Or, well, yeah. this is another large speed up on general emulation. Large improvement to general emulation performance. Cool. Yeah, so let's do STOSB and see how we would do that. So STOSB, that's store string byte. And the way it works is, let me show you the Intel instruction. Wait, what is the alphabet? STOS. Yeah, so this is STOSB. It's just a single byte opcode, and all of the operands are implied. So basically it's store AL at address ES and then DI or EDI depending on the address size of your instruction. And yeah, here is the pseudocode for the implementation. And we are looking at this one right here. So if the direction flag is 0, then we're moving forward in memory. So if direction flag is 1, then we're moving backwards. So typically in like compiled programs these days, you don't see the DF being set. So you're almost always like stossing forward in memory. So I think we'll have it like a fast path here, like if not DF, fast path for memory fill, 8-bit memory fill. Maybe let's call it 8-bit forward memory fill. So, and then we can like try to do this. So fill memory 8. Yes, and then we need the destination index. So destination index is just a helper that gives us either DI or EDI, depending on the address size of the instruction, because Intel instructions are amazing and you can do stuff like override one instruction so that it's a 16-bit address instead of a 32-bit one, and then the next instruction goes back to 32-bit. So we have to keep track of that kind of stuff. So fill memory, and then we need the size of the range to fill. So that's an ECX, because, or actually that's only if this is a rep opcode. Okay, so if we have a rep prefix, right. Otherwise, it's just a regular a single STOSB. That means like store one string byte. But if it has a rep prefix, so it's rep STOSB, then it means do this like ECX times and advance. The destination index by ECX. That's what we have to do. Right, okay, so the thing to fill with is in AL. So if that succeeds, then we have to do some stuff, otherwise we will fall back to this generic path here. So let's see. Yeah, this is fine. I'll give it shadow U8. Okay, so we don't need to pass a full logical address. We can skip the segment part of it. Oh, I was looking in the wrong class here. All of these guys use the logical address. Okay, I don't want to be different, so maybe we'll do that anyway. Fine. Okay, and then it needs to return success or not. Okay, good. So how do we implement this? I guess, well, if size is empty, then we can say that that worked out fine. And otherwise, we need to find a region. So region is find region for address. If we don't have a region, then let's just say that it failed. Fallback path will take care of it. And then if region doesn't contain the address plus size -1, that means that the full range is not contained in the same region, so we'll just skip over it then as well. No fast path for you. So in fact, maybe we should rename this to, I'm thinking like fast fill memory 8. Because this is a fast path and it can fail, and that's okay. Okay. So now we have the region and we know that it contains the entire span. So now we need a data pointer, which we don't have, but we'll add soon enough. So value, data plus offset in region maybe, size. And the shadow data needs to be memset with the shadow value and then return true. Okay, and the offset in the region is going to be address offset minus region base. Yeah, that makes sense. So then we just need to be able to get we need to be able to get the data pointer and the shadow data pointer. So how about we just add virtuals for that, like virtual U8 data. We'll make it pure virtual, so everybody has to implement this. That's probably okay. And oh, memset is undeclared. Okay. So simple region. Let's just go. Oh, yeah. So we just have to make those existing members virtual. Nice and easy. And map region, same exact story. Shared buffer region has data but no shadow data. That's cool. Right, so now we have to take care of this. So if this succeeds, we have to, ECX goes to 0 when this happens, actually, I forgot about that. So set ECX. I think this is also address size dependent. I'm pretty sure. Decrement loop index. Yeah. Okay, well, we don't have to be super tidy here, so we'll just branch. You could make a helper for this, but I think we don't need one right now. Okay, so we're updating ECX, and then we just need to advance EDI or DI by ECX or CX number of steps. So set EDI, EDI value plus ECX value, and we'll take the shadow from EDI so that if EDI was uninitialized data before, it is uninitialized data now, just, you know, uninitialized data plus ECX. I wonder if ECX should taint EDI here if we're looping an uninitialized number of times. I don't know. Should uninitialized ECX taint EDI here? I'm not sure. Something to think about. For now, we'll just use the shadow from EDI to taint. Yeah. Okay. I wonder if I got everything right here. I feel like slightly confident, but we'll see. Okay, runs id. Runs browser. It's not significantly faster though. Shutdown is still pretty slow. See if we can get a profile. Just a profile scrolling up and down is good. So we have stasd right here. Stasb down here. Stasb is still calling write 8. Seems like we're attempting to do a fast fill memory, but maybe we're failing. Let's log something here, so debug line. And then contain within region test. Yeah, because I feel like we shouldn't be seeing those right eights. That would be down here. Oh, we are going fast. Well, that's good. Oh, wait. This is if not. This should be if it succeeds. So we're doing the fast path and then acting like it failed. Yep. Very silly. Okay, so here goes our thing. Okay, so it is slightly faster actually. Very cool. Let's see if we can see STASB in a profile. STASD still up top, but where has STASB gone? Well, we're gonna need a find feature in Profiler because STASB has moved all the way down here. Okay, so it's down from 2 point whatever percent to 0.09% of runtime. That's really kick-ass. Now, and we can do the same thing for STASD, of course, which we should, but probably not going to do that in the video because it's kind of mechanical and just doing the same thing. But we are missing one thing here, which is the malloc audit. So that's going to cost us a little bit. So we're not quite home free yet. Let's see, so how do we do that from here? It's that if it's an mmap region and const, I guess, is malloc block. If it's a malloc block, then if the emulator has a malloc tracer installed, then I think we're gonna have to do something like this. Or wait, hold on. Yeah, so we'll just do this. Tracer audit right. This is really sad, but I'm just doing this to make the code kind of copy pastable for later. And then really this should be like a single call instead of a loop. So fix me. Add a way to audit an entire range of memory instead of looping here. Yeah, so this is kind of stupid. Like we're gonna do malloc access audit for every single byte. But this could be improved by just adding a mechanism for auditing an entire range in one go. But I think this will probably not slow us down that much already. Yeah, just maybe just a tiny bit. Let's see. Just see what happens with it. Do we have STOSB anywhere? STOSB is here. 0.49. Yeah, okay, so it's still way better than 2 point whatever percent, but it's also worse than no audit, but that's to be expected. I think I'll leave this in the fix me state for now. Something to improve on. And generally, I think we're gonna be good here for today. So let's just commit this. First off, let's do all of these, adding the data and shadow data accessors to regions. Add data and shadow data to region. Yeah, okay, good enough. And then this guy right here, so a fast path for rep STOSB, forward rep STOSB. This is used by memset in so we get a lot of mileage out of optimizing this instruction. Note that we currently audit every individual byte accessed separately. This could be greatly improved by adding a range auditing mechanism to malloc tracer. Still, that's very nice. I wonder if we could get that thing to go under the 1300 mark. Maybe we should have a way to kill this thing faster also. Right now you kind of have to wait for the leak report. Would be cool to see 12 something. I'm just gonna hack 32-bit one quickly here, just see what it would look like. Something like that. this could probably be generalized somehow. But it doesn't really stand out to me right now how to do that nicely. Don't always have to generalize everything right up front. Sometimes you just have to get things done, and then you'll think of better ways to generalize them later once you get kind of comfortable with them. Come on, let's see a 12 something. Oh, that went so bad. Oh, wait, cripes. I can't just use memset blindly like that. We have to do a 32-bit fill. That's okay, we have fill. Wait. We have some helper for that. Fast U32 fill, that's the one. I guess size here is not size, it's rather count. And then this has to be like that. And we want to fill the shadow data. What am I messing up? Maybe nothing. Definitely messing something up. Okay, maybe I was going a little too fast. Not really thinking about what we were doing here. So it's a fast memory 32 fill, sure. Putting EAX at ESDI, sure. ECX times, sure. That's all good. We need to increment EDI by ECX times size of U32 in this case. Right. Because we're going 4 bytes at a time, not 1 byte at a time like stas B. Yeah, so we just ended up with DI or EDI with the wrong value after this instruction. That should work better. No? Okay, what else are we messing up there? Same prototype as memset, sort of? Sure. Is it the audit thing that's whining? And everything else is fine? Okay. So it's just whining. Yeah, because what am I doing with my math here? I'm like multiplying twice. Or going too far past the end. Yep, that'll be it. Then it's not in the 12 something. I thought it would dip below. Seems like it doesn't, but let's get a profile regardless of just a little bit of scrolling. A little bit of scrolling, see what happened to STOSD. Wait, where'd it go? Did I miss it? Here's STOSB. I'm not even seeing STOSD. Here it is. Oh my goodness. Okay, so he was reduced to a small fraction of his former glory, but even so, that was not enough to actually bring that load time number down. Although that might be for any number of reasons. I mean, this load time is calculated inside the emulator, so it's not super exact or anything. Anyways, it's cool to knock those functions down, and we can see now that audit read is pretty high up here. And both of these should be audit write, actually, aren't they? Audit write, yeah. So maybe we should have some kind of filtering or search mechanism in the profiler, because it's kind of annoying looking for a function if you can't see it. Anyway, audit read is 7% of runtime, so we can probably improve that, but we don't have to do it right now. I guess we could take advantage of the page mapping we made. We can take advantage of that in the mallocation lookup that we implemented yesterday, because there we added a hash map that stores the malloc chunk block metadata. But now that we have a an array of all the regions, we could potentially reorganize that a little bit, and then we wouldn't even have to do a hash lookup here, because you can see that hash lookup, while it runs in constant time, it still takes a while to run, right? Like an array lookup is going to be much faster here. So many interesting opportunities to improve on this. Anyway, I'm happy with what we have here, so I think we're going to call it a day. Down from 1.6 something to 1.3 something seconds. Anyway, this is it for today's video. So this was another user space emulator internal optimization stuff. I hope that you found some of it interesting. I think this is a space of many interesting problems and trade-offs and things, so it's fun to work on. And thank you very much for checking out the video. I hope that you liked it. And what else do I normally say? I'll see you next time.